So for our first talk, we're going to have actually a tandem talk, both by Assistant Professor Baptiste Le Bihan, coming from University of Geneva. And then the second part of the talk, I believe, it's going to be given by Enrico Ciniti, who is also still at the University of Geneva, but soon to move to University of Amsterdam to work with Sebastian De Haro. Okay, the floor is all yours. Thank you.
Thank you very much for the organization of this wonderful event. I think it looks like a great format, so I'm very curious to experiment this. So in fact, I'm going to give the first part of the talk. Enrico will speak in the middle, and then I will conclude the talk. So in this talk, we really try to present a few discussions and ideas from philosophy, but trying to make them accessible to physicists. So the talk might seem a bit in between at some points, but I hope you will like it still. All right, so Spacetime Emergence, Revolution of Footnote. All right, so the claim that spacetime is emergent from a more fundamental non-spatiotemporal structure appears in many approaches to quantum gravity, as you know, in string theory, in group field theory, in LQG, in CST, and many more. And these approaches put under pressure space-time structure in different ways. For instance, by quantizing space-time, and this could mean several things. In group field theory, by introducing non-spatiotemporal atoms, in holography and string theory, or for instance, in causal set theory, by trying to replace space-time by a set of causal relations with no meaningful notion of distance between the elements in the system. And so these approaches suggest that different properties we usually associate to space-time, in some sense, disappears in quantum gravity. So now the claim might appear trivial. Perhaps it's just a reduction, like temperature from molecular behavior. Or maybe it's just a catchy slogan to secure grants and to appeal to the intuitions of the grant provider. Well, we want to argue to the contrary, and that there are many interesting possibilities. But what we want to do, because we are trying to understand, yes, what are really the risks of space-time emergence or emergent geometries? What are the risks of this being just a kind of a catchy slogan with no really interesting physical or philosophical implications? And so we started to think a bit about how to organize, how to rank in terms of radicality, different kinds of, different scenarios of space-time emergence. So what we are going to do is to propose a particular classification to discuss a bit more what those different scenarios mean, both for physics and outside of physics for philosophical debates. Let me just introduce a few ideas from philosophy, especially for the physicist, as I have experimented some kind of past disagreement on the use of those concepts or words. So as philosophers, we always love to talk about existence, about things existing. And at least in this talk, it will be taken as a brute fact that something exists or not. And there is not really anything more to be said about what existence is. It's a primitive idea. But we don't mean by existence measurability. So for philosophers are really flexible. They don't mind talking about the existence of non-observable, non-measurable quantities, for instance, theoretical quantities that you can calculate. But it could be many more other things. And so philosophers really talk about ontology, which is a list of things that exist. So ontology is used in many contexts, but you can think of the ontology of physics, what exists in the physical world, the ontology of mathematics, what exists, if anything, in a mathematical domain. But you can have other things, the ontology of biology, the ontology of whatever you like. And then you can also talk more in the abstract, talk about what there is, what exists, sorry. Or you can also relativize the ontology to a theory and say what exists according to a particular theory. For instance, the ontology of Bohmian mechanics, what exists according to Bohmian mechanics, or the ontology of GR, what exists according to GR, if GR was true and fundamental. And we usually also distinguish between ontology and epistemology. And epistemology is more about knowledge, how we produce knowledge, either ordinary knowledge or more interesting for us, scientific knowledge. Right, so I just wanted to give you some pointers, probably would be quite helpful to disambiguate some future discussions over the week. All right, so space and time, or geometries, what are we talking about exactly? And I think it's quite helpful when you approach those ideas in physics of space-time emergence to distinguish between two parameters. First, what there is at the quantum gravity level, so the ontology of your theory of quantum gravity, if we were to put our hands on one. And second level, what we want to recover at the macroscopic level, say relativistic space-time of general relativity, perhaps quantum field theory, scientific cosmology, or the phenomenology. Interesting note here about the phenomenology. So phenomenology is a word used both in physics and in philosophy in different sense. I think it's quite interesting to have both in mind because they are both relevant for questions over space-time emergence. So in physics, phenomenology is really about making contact from with the world, with the empirical world, from the theory, so building bridges between a theory and experiments. In philosophy, it means something a bit different. It's about more perceptions, what you might call the analysis of our mental content, of our perception, of our mental life, the way things appear to us. So if you know already a bit about this topic, say, take the problem of empirical coherence, quantum gravity, it's more about phenomenology in the physical sense, prima facie at least. But it could also be phenomenology in the philosophical sense might also play a role if you think that space and time are first and foremost subjective. And so what we really need to do is to relate psychological experience of space and time to a non-spatial temporal ontology, and not necessarily an objective space, objective time, or objective space-time to the non-spatial temporal domain. So yes, I thought it would be interesting to mention that for the discussions. So what exactly is denied fundamentality or reality? Also interesting distinction. When it's said that space-time is not fundamental. In other words, what are the defining features of space-time? Because as I mentioned, there are two levels really, right? There is a level of quantum gravity, but also the level of what we want to explain in the macroscopic world. That will be a big part of this talk, right? Trying to understand, sorry, just going back, trying to understand what there is a fundamental level, at the derivative level, and also how to relate those two levels. So in fact, there are three really interesting questions. What you do have, what we do find at the fundamental level, what we do find at the derivative level, but also what is this talk of levels really meaning? Is that just, we're just talking about this different descriptions that are more or less accurate, or is it a bit more, right? And to have this discussion, it's really important to kind of agree on what we mean by space-time, and that's, as we will see, it's very difficult. And one methodological issue I want to mention already is that it's not completely clear where the threshold is between space-time elimination and space-time revision. So at which point when you start changing, replacing some of the usual properties of a fundamental concept, do you decide that the concept no longer apply and in fact we eliminated the concept, right? So at which point when you start changing the properties we usually ascribe to space-time, do you consider that in fact space-time no longer exists because there is something else instead? So I think it's in large part a matter of conventions, but not only. And one thing we are going to do in this talk is try to find to propose a more objective criterion to distinguish between space-time elimination and space-time revision. And Enrico will present this. All right, so space-time as a structure, right? There is an interesting question about the existence of space-time and the relation of space-time to space and time. So you might think that the interesting action is happening at the level of space-time, and what we really need to identify are the necessary sufficient conditions for the existence of space-time. So perhaps, so Niels was suggesting this idea, so I mentioned a paper we wrote together, but that was really his idea. Maybe the defining feature of space-time or minimal space-time is to have locally in space-time a local separation between a local split between spatial directions and temporal directions, or something perhaps a bit more minimal, quasi-space or quasi-time if we need to remove some of the properties we usually ascribe to space and time. But of course, if we start to ask this question and we propose this answer to what is space-time. Space-time is this kind of structure that have locally a distinction between spatial directions and or space-like directions and temporal time-like directions. Then there is this question, exactly how do we think about the relation between space-time and space and time? So philosophically, people distinguish between unitism, the idea that space-time is more fundamental and space and time don't really exist or are abstractions from space and time, and separatism, which is a view where you really have two manifolds. Of course, because of the huge weight of generativity, the standard view is unitism, the idea that we are really living in a space-time and not in a world made of space and time. But of course, if you move from generativity and if you zoom out and want to ask what is space-time according to physics more generally, and based on our speculations in quantum gravity, it's not completely clear whether we should necessarily connect space-time to relativistic physics, right? And here I think there is an interesting question. Do we want to connect the concept of space-time to relativistic physics? Or do we want to be a bit more liberal and accept that there may be space-times that have nothing to do with relativistic physics, right? So you might think of Newton-Cartan space-time, basically this reformulation of Newtonian mechanics by using a space-time manifold. And my impression is that there is no really, you will tell me if I'm wrong, but I don't think there is any consensus among physicists about what could be space-time. It really depends on the context of discussion. Right, so now moving from space-time to space. Also something I want to say that the difference between philosophers and physicists is that philosophers are very happy to put things on their slides they don't believe in, right? I guess my understanding that physicists usually try to have more factive things on the slides. So right now what I'm doing is putting a lot of conceptual distinctions, a lot of ideas. It doesn't mean that I buy into everything I said, and especially in the next slide, because what I'm going to do is to give what I want to call the ID card of space. So what is space-time according to different people, but also according to the layman? What is space naively before we start doing physics? Why? Because I think then it helps us to really focus on the ordinary properties of space we are denying reality to. Right, so let's set aside phenomenological space or subjective space and think about the physical space. Well, the core property of space is to locate things. So one thing can be between two other things. So there is some ordering of things or events. More peripheral properties are continuity, discreteness, right? Or is it or topological properties? Is it open or closed? Substance or relations? You have this big debate going back to Newton and Clark, Leibniz, on what exactly is the relation between space and matter, that we can translate as a debate these days about what the relation between space-time and matter or the matter fields. Do you need one to have the other? Which is more fundamental than the other? Are they both equally fundamental? Those kind of questions. They seem tangential or peripheral, but in one thing you might think that being a relationist about space-time is already being an emergentist about space-time. Some people are thinking like this. I think it's not really doing justice to the phenomenon of space-time emergence in quantum gravity, because usually people have something stronger in mind. But in a way, yes, saying that space and time are not really substances or don't have an existence on their own, it might feel a bit like a particular kind of minimal kind of or weak kind of space-time emergence. Right, so time basically inherits a lot of its properties from space. Setting aside again live or subjective time, we can ask again, are those properties of before-after relations real? Are those relations of simultaneity real? So relativistic physics put pressure on simultaneity, but not on before-after relations. Because you have the time-like relations. But when you move to quantum gravity, take loop quantum gravity, disordered locality, it's not entirely clear that it's always fixed what are the before-after relations, and that seems to be a core property of space that we may be attacking. Again, we have the peripheral properties, continuity, discreteness, open or closed, substance or relation. But then, of course, time is quite different from space, so we also have some specific features, right? Not shared with space, potentially the passage of time, the existence of a direction of time, either intrinsic, more embedded in the manifold, or extrinsic, inherited by the dynamical laws. So I mentioned those A, B, C theories, which are theories of time in philosophy. If you know them, that's great. If not, not a problem. Basically, that's the classification made by philosophers to distinguish between theories of time where you have passage or not passage, and whether you have a directionality or no directionality. But yes, so it's again an interesting question. Which of those properties are under attack by quantum gravity? And you have the relation to change and motion, which is related to more or less to the passage of time. So hot debate in philosophy as well, how you want to relate the concept of change or the concept of motion to the passage. Do you need passage or not to get change? Usually people think that no, we can have time without change, and even time without passage of time. All right. So as I said, all those properties of space, time, and space-time are possible targets for a theory of quantum gravity. And as such, spacetime emergence can be more or less radical. And usually quantum gravity, which will be QG, goes further than GR in denying core properties of space and time and possibly space-time. And everything I said is kind of like a huge list of open questions on what are actually those properties at the fundamental level. So it's more to put content on the table. And right now, what we are doing in the second part of the talk is to discuss two methodologies for developing a theory of quantum gravity and see how those two methodologies lead to different differences of for space-time. By this, we mean two different degrees of radicality in denying the fundamentality of space-time. Right. Okay, and then last part of the talk will be discussing some implications for big questions outside of physics. So a bit. Let me say this: like where exactly the limit between physics and philosophy is a bit open, so we don't put a lot into this classification. So some of the things we are going to discuss in the metaphysics section could be counted as being part of the physics. So I don't think that's a big statement we're making. It's just a conventional classification. But we are going to talk about what are the implications in physics, for instance, for thinking about dimensionality, but also outside of physics for multiverse scenarios, or for thinking about the nature of consciousness or abstract entities. So trying to have a broad map. Also one last point, we're not going to talk about laws of nature and causation, which might seem a bit weird because my current grant is on causation, quantum gravity, and because a lot of the discussions are on laws of nature. But it was more in the spirit of opening new topics that we decided to focus on different categories and phenomena and not to focus on laws of nature and causation. But of course, it's some exciting topics that we really want to talk about. And now I'm going to hand it over to Enrico for the second part of the talk.
To give me this, I'm probably gonna use it terribly. But I'll do my best not to gesticulate too much, which as an Italian person you can understand it's gonna be really difficult. So yes, thank you. Happy to be here. Thank you to the organizers, and I'm gonna pick up basically where Baptiste left off by kind of telling you about this. Two different ways that we think a theory of quantum gravity can approach the task of reconciling general relativity with quantum mechanics, which broadly speaking means that there are two different ways in which we think that a theory of quantum gravity can approach the task of dealing with space-time and telling us what happens to space-time once we try to give a quantum description of this thing. And the two views that we have in mind are called, one we call it generalization, in the spirit of being maximally controversial. We call it generalization. And the idea is that under generalization, what one does to account for the quantum nature of spacetime is expanding the array of geometric structures that the theory has in its arsenal to include notions that one could broadly characterize as quantum geometry or quantum spacetime or whatever your favorite notion of geometry with quantum in front can be. And an example, again, in the spirit of being maximally controversial, of this strategy, at least to my mind, is something like loop quantum gravity, where one starts from a classical description of GR spacetime and then basically tries in various ways to give a quantization of this classical GR description. And the other strategy that we have in mind is called replacement. And the idea behind replacement is basically that instead of generalizing the structure of GR spacetime to account for quantum effects, we will replace GR spacetime with some new or different geometric object, and we will use that new object to construct the relevant quantum theory, and then from that thing, we will recover spacetime. And examples in this vein are things like group field theory, string theory, and holography. In some sense, the origin of this distinction was in making sense of the fact that people in holography and people in loop quantum gravity both talk about spacetime emergence. And every time one reads a paper from one of these two communities, they seem to have very different things in mind, but they use the exact same language. And the idea is exactly that they have these two different things in mind to some extent. So the idea here is that generalization and replacement, as I was telling you, are methodologies for building a theory of quantum gravity. They are methodologies for, as I was telling you, dealing with space-time once we move to a quantum level. But of course, in the background of this and in the spirit of wanting to get some metaphysical insight from these two approaches, one could think that one of these methodologies might be more promising in latching onto the physical structure of reality. It might be a better way to get to what is actually really there. And we will call the claim that one methodology actually, that the belief that one of these two methodologies does latch onto reality better, the claim that this methodology is factive, unlike the other, of course. And so the idea behind this factive terminology is just that the methodological success, so the success, for example, of something like holography, would reflect a fact about the underlying physics. The success of applying replacement would reflect some fact about the underlying physics, and so the reality itself. Now, the two approaches, in some sense, are presented in a rather cut and dry way. There is a broad heuristic to distinguish between them. That is at least, I think, how we want to think about them to get some sense of when it is a case of generalization and when it is a case of replacement. And the idea is simply that to distinguish between two options, we can ask whether or not spacetime is recovered simply by taking a limit, or one needs something more. And the idea here is that generalization encodes things like spacetime emergence in terms of limit relations. And again, here the prototypical example is something like loop quantum gravity, where recovering spacetime basically amounts to taking some form of classical limit. Replacement, on the other hand, is going to require, in our mind, more than limits, because the idea is that we are not starting even from the spacetime of GR. We are replacing the spacetime of GR with something else and then constructing a quantum theory out of that, which means that we can't simply take then the classical limit of our theory, because we will get back, at best, the thing that replaced GR spacetime with, not GR spacetime. And here again, an intuition can come, if you're familiar with it, from holography. And the idea is that in holography, for example, we do not really just take a semi-classical limit. If we want to recover spacetime, we usually have, in some sense, and the phrasing is left deliberately vague because it's a philosophically and conceptually non-trivial question, but we have, in some sense, to go through the duality map. For example, by doing things like entanglement wedge reconstruction. Now, in some sense, again, the idea here is that which approach a specific theory of quantum gravity is going to take to this, whether or not they're going to be an instance of generalization or replacement, is going to be some kind of fundamental methodological question but also, especially if one accepts this claim of activity, that it's going to shape profoundly how we think about the underlying physics and metaphysics, in particular, of our theories. And the idea here is simply that what is fundamental and what is not fundamental, and how we describe the fundamental and the non-fundamental, of course, is going to shape and justify specific quantum gravity methodologies and specific metaphysical insights that we can draw from our quantum gravity theories. So as I was telling you, generalization is going to be a methodology common in examples from loop quantum gravity and things like canonical quantum gravity, basically any approach that we can categorize under the broad umbrella of we are quantizing general relativity in some more or less broad sense is going to, broadly speaking, count as an instance of this. And it leads to a very natural and elegant view of spacetime emergence, where spacetime emergence is going to be mediated by the same limiting relations that are familiar from many other areas of physics. It's going to be, emergence is going to be represented by a limit, just like in most other situations in physics. It's more conservative exactly because of this, because we're saying that spacetime emergence at the end of the day is analogous to what you might think of as more mundane kinds of emergence. An example here that I think Rovelli and Vidotto use is that the intuition in loop quantum gravity, for example, is that the emergence of the classical gravitational field, spacetime, from its quantum counterpart should ideally be analogous to the emergence of the classical electromagnetic field from its quantum counterpart in QED. Now, replacement, on the other hand, seems more common in theories like string theory and holography. And in string theory, for example, the idea is that we would not start from a 4D spacetime, but rather from some 10-dimensional superspace. We are adding supersymmetry, further dimensions, and other fancy gadgets on top of this. There is also the use of things like schemes and other notions coming from algebraic geometry that are very common in string theory, that have relatively little connection or little obvious connection to the Lorentzian geometry of general relativity. In holography, it's even more clear, of course, what's going on, in the sense that we treat GR spacetime as equivalent to some kind of conformal field theory living on the boundary of our ADS spacetime. And then what we do is that we can quantize this conformal field theory and produce a relevant theory of quantum gravity. Again, here what we do in some sense is that we replace GR spacetime with something else and then work on that thing. As a consequence of this, the idea again is that under replacement, spacetime emergence will not then be mediated by a limit. There will not be just a limit at the very least, but something more than a limit is necessary. There's going to be some more complicated machinery involved, entanglement wedge reconstruction in holography, some notion of compactification and supersymmetry breaking in string theory to get back the 4-dimensional Lorentzian manifolds of general relativity. And this often leads, as one might be familiar if you know string theory or holography, to rather theoretically more complex approaches to quantum gravity, significantly less minimal and conservative than something like loop quantum gravity, which is really just very focused on giving a quantization of the gravitational field. And this is going to be, as we are going to see, especially clear on the metaphysics side of things, because it is going to be a replacement that is going to sanction in some way many of the more revisionary claims that people oftentimes want to make on behalf of spacetime emergence. So I've told you a bunch of things about these two different methodologies. I've told you that they have something to do with the underlying metaphysics of our theory, that they are supposed to teach us something about what the world looks like. I haven't really told you to go back to Baptiste's initial distinction of various concepts that come from philosophy. I haven't really told you much about whether or not these methodologies think, for example, that spacetime exists. They think that it does not. What do they think? So to start, let's draw some distinctions about what happens at the fundamental level. We think that there are basically three different options for what might be happening at the fundamental level in quantum gravity. One we call F for fundamental eliminativism, and the idea is simply that spacetime does not exist at the quantum gravity level. There is a notion of fundamental revisionism, and here the idea is that spacetime exists, but differs significantly from what we thought it was. And one can think here of different sorts of scenarios. One could think of having some kind of discrete general relativistic spacetime. or for example, some kind of quantized space-time where we might have some notion of quantum indeterminacy playing an important role, but still intuitively one might want to say that just like for a normal quantum theory, the fact that we lose, the fact that we have some notion of quantum indeterminacy does not lead to the disappearance of the electromagnetic field. It just becomes a quantum electromagnetic field. The fact that we have indeterminacy in space-time doesn't mean that space-time disappears in this very strong sense. It just means that it's a quantum space-time. And then kind of the most boring option of all, but it's worth having it at least for completeness, is this notion of full-blown realism. And here the idea is just that space-time exists. It does not differ significantly from what we think it is. It is fundamental. You know, we thought we would get something new by looking at quantum gravity, but we happen to be wrong. And here is a convenient picture to think about this. Of course, then if you're a full-blown realist, you're basically in the business of saying that the fundamental level here and GR spacetime stand in some kind of identity or at least very close approximation relation. If you are a fundamental revisionist, you're in the business exactly of saying that they stand in some relation of revision or refinement, so where we actually change what spacetime is, but we don't hit a threshold where we want to say that it's not spacetime anymore. And then if you're an eliminativist, then you're in the business of saying that you need some very strong notion of emergence or some building, grounding notion to make up spacetime from something that has nothing to do with it. Now, moving to the non-fundamental level, we talked about what happens at the fundamental level. Both elimination and revision at the fundamental level are compatible with different views at the emergent level. So they can basically account for different opinions for what happens to spacetime at the derivative level. So GR spacetime or even ordinary space and time might still emerge in a robust sense or fail to do so, which means that we basically distinguish between two options also at the derivative level. One, we call it derivative revisionist, and the other one, we call it derivative eliminativist. Of course, in some sense, we do not really have a derivative full-blown realist because, as you can remember from the picture, it's an identity claim, which would make it rather trivial to claim that one is a derivative full-blown realist because, you know, you were anyways. So we can call these two options basically de-eliminativism and de-revisionism in analogy to the fundamental claim. So one could be an eliminativist at the derivative level, or one could be a revisionist at the derivative level. And if there are really two distinct structures, so one fundamental and one derivative, then the idea is that these are going to be connected with different kinds of building relations, what I was hinting at before. Some notion possibly of composition, some notion of grounding, some notion of functional realizations. Again, the philosophical literature is rather replete with different ways of analyzing these kinds of claims, and you can definitely have a field day in looking at all of them. I don't recommend it. Now, going back to the actual point, so we have kind of developed two different pieces of machinery. We have developed a methodological, let's say, piece of machinery which distinguishes two different ways in which a theory of quantum gravity can approach the task of dealing with general relativistic spacetime in a quantum context. And we have told you a bunch of different ways in which one can think of the fundamental and derivative ontology of spacetime in the context of theories of quantum gravity. Now we would like to bring them together because the idea is that these methodologies are going to tell us something about the underlying ontologies. And the idea is rather straightforward at this point, which is that if one is going to think that generalization is factive, then we are going to get something like fundamental revisionism, because the claim of generalization, as we said, is the claim that we are generalizing GR spacetime, adding structure, changing what it is in order to accommodate quantum effects, but we are not really getting to the point where we are just replacing it with something else. Exactly. So the idea is that not that we revise of course, importantly, the idea here is not that we revise the concept of spacetime at the derivative level of description. Spacetime, in some sense, remains fundamental in the sense that we are not removing spacetime from our fundamental ontology, but it's rather that in some relevant sense, it's different from the spacetime of GR. The operative intuition here is that it becomes something like quantum spacetime. So it still makes sense to say that at the fundamental level, there is such a thing that we are happy to call spacetime. It's just that it's not GR spacetime, it's quantum spacetime. One might be rather strict about what they mean by emergence and claim that this is not a case of emergence properly speaking, because we should call spacetime emergence only the strongest possible option and not this rather weak and more mundane, as I was calling it before, option. I personally think we can get by saying that this is rather best categorized as some slightly weaker or less radical form of spacetime emergence. It still makes sense to say that there is some emergence happening, just like it makes sense to say that classical physics emerges from quantum physics, but we don't want to say that it's the most radical option. And of course, to the contrary, if replacement is factive, then we are going to get something like fundamental eliminativism. We could still have some revision of spacetime at the derivative level, so we could still have derivative revisionism, but we accept that in some relevant sense, in a very strong sense actually, spacetime is nowhere to be found at the more fundamental level of description. We are just not dealing with anything that has anything to do anymore with spacetime at the fundamental level under something like factive replacement. So, implications, since that's kind of what we are trying to do here. If fundamental eliminativism and so some notion of active replacement obtains, as we have defined them, they do rather clearly entail some notion of revolution, to go back to our title, in physics. This is a rather different notion of emergence. It's a rather different notion of how the fundamental is connected to the derivative and the relation that the quantum theory stands to its classical counterpart than we are used to from other quantum theories. In this sense, at least, it seems fair to call this a revolution. It's a new thing, and we have to develop new ways to think about it, and it could radically change how we think about a lot of things in metaphysics. It means that spacetime either does not exist at all, or that it exists only as something grounded in something deeper, in some deeper non-spatiotemporal structure, which has very little relation with the macroscopic phenomenological world that we are used to, even from just something like general relativity. Now, what about fundamental revisionism, and so what about generalization? If this were to obtain, does it mean that then spacetime emergence, downgraded to mere revisionism, becomes a footnote rather than a revolution? Have we kind of discovered that at the end of the day, it was not that special what we were doing, despite what we thought? We don't necessarily think so. We think for physics still, it's going to be an insightful and surprising discovery about the structure of reality, that there is a quantum theory with geometric variables and that it stands in a specific relation to its classical counterpart. And for metaphysics, again, this is going to be more of a case-by-case problem. It's going to depend on exactly which spacetime features we revise. Because going back to what Baptiste was saying before, if, for example, in going through our revisionism, we revise quite radically what we mean by time, that might have very deep metaphysical implications. If all that we revise is that we say that spacetime becomes discrete rather than continuous, then that might be significantly less impactful on other metaphysical views. So when it comes kind of to give the metaphysical outlook here, when it comes to metaphysics, fundamental eliminativism appears to have far-reaching implications for broader metaphysical issues, and this warrants a dedicated treatment of those implications, while for fundamental revisionism, metaphysical implications have to be examined more on a case-by-case basis. It's going to depend on exactly which specific model, which specific form of revisionism actually takes place, exactly what we can get out of it. So overall, to kind of wrap this up, we believe that fundamental eliminativism, and so replacement, entails drastic consequences, whereas revisionism, so generalization, remains more conservative and offers weaker motivation or a case-by-case at best motivation to pursue radical metaphysical conclusions. Now, just to give a a starting point for what kind of metaphysical conclusions one might draw, since we've said a lot about the fact that one might draw this, but we haven't said which ones you might want to draw. Let's look, for example, at the case of how many dimensions does the world have. And the idea here is that, especially once one starts dealing with replacement and strategies like this, one gets quite quickly and quite easily diversified counts of how many dimensions the world has. So in GR, of course, we have a 4-dimensional spacetime given by a manifold plus a metric. In string theory, in all its varied forms and constructions, we go from a 10-dimensional supermanifold to an 11-dimensional supermanifold to even a 10-dimensional supermanifold with two time directions and 10 space directions in the context of F theory. And of course, the possibility of having compactification, for example, changes even the effective count. So in string theory, we are happy to say that we might have a fundamental 11-dimensional spacetime, but we might have an emergent 5-dimensional spacetime, 7-dimensional spacetime, 3-dimensional spacetime, 1-dimensional spacetime. If you're really fancy, you can even try to think about 0-dimensional spacetime. And of course, we also have dualities. We have things like T-duality that swap large and small radii, and in particular, of course, the SCFT holography, which pair in one of the canonical examples, something like a 5D bulk spacetime with a 4-dimensional boundary CFT, while preserving all kinds of empirical content and theoretical content, so by treating them as equivalent, which again points to the fact not just that we might have different dimensions, but that the notion of dimension might not even make a lot of sense at the fundamental level, since we are talking about an equivalence between two different dimensionalities. So there seem to be two options here. One is the idea that there is some notion of derivative dimensionality. Dimensions belong to the emergent or phenomenal spacetime, and the fundamental base is just purely non-spatiotemporal. It has no well-defined notion of dimension. There is no fixed notion of dimension. And there is a notion of perspectival dimensionality, for lack of a better word, which is the idea that basically we can have something like a duality, for example, and different duals are going to fix different dimensional descriptions, dimensional gauges of one underlying structure, which might, for example, be relevant upon taking something like a semi-classical limit, for example, or some kind of limit. They might be different entry points into a fundamentally non-dimensional structure. So the upshot in some sense is that when we ask how many dimensions, we can only ask that at the effective level at which we are working with, at the fundamental level, dimensionality may very well be undefined or not a property at all. Now, other possible implication before I leave the microphone back to Baptiste. Multiverse scenarios in cosmology. We have like a broader template for how to think about multiverse scenarios. The idea is that one can have universes, bubbles that can be disconnected at the emergent spacetime level, in the sense that there is no nice spatiotemporal trajectory that connects them, and yet remain in some relevant sense, for example, causally connected by having some kind of non-spatiotemporal base. And the distinction here is basically between something that we could call holism and something that we could call fragmentation. So fragmentation would be the case where there is disconnection all the way down. These are just quite literally disconnected universes. There is nothing that connects them. While holism accepts that these different bubbles might be might be spatiotemporally disconnected, but might be connected to something else. In this sense, there is some holistic structure underlying them. And of course, if you have fragmentation, then one consequence of this is that there is going to be no hope of having any type of empirical access to the claim that we are living in a multiverse of this kind. But if we have a holistic multiverse, we might actually use this non-spatiotemporal structure to gain access to some evidence for the claim that we live in something like a multiverse. And like two rather simple examples, here again in string theory, for how this holistic multiverse might be realized. one idea is that one could have two different dual spacetime emerging from a single common core. So the idea is that we have replacement by dualities, and then we have two limits where we have distinct universes that are then connected by the underlying common core. Or maybe even more straightforward in string theory, the idea that we could have moduli fields that can be varied in order to connect two classically distinct solutions. So we might have two different supergravity solutions, and in string theory we could act on the moduli fields of the theory, which are basically parameters, and change them until we move from one solution to the other solution. And that would be a process that, for example, in GR would not have any obvious analog, but in string theory we could. And so the idea here is that we could have replacement by some non-spatiotemporal or non-GR structure in the form of these moduli fields that allows us to access different universes in some sense. So now back to this. There you go.
All right. So now, just to finish quickly, it was a lot of content, branching many directions. So I'm going to branch a bit more, but try to be to keep things quite simple. So when you start thinking about the metaphysics of the extra physical, so what I mean by that is what is not physical, properly speaking, but still related to the natural world in a very deep sense. So we're going to talk about consciousness and abstract entities, mathematics, if you want. So we think that the fact that space-time might fail to be fundamental in the strong sense, corresponding to the replacement strategy, may have interesting implications for the debates over the nature of consciousness and the relation between consciousness and the physical world. Why? Because there is this important problem in the philosophy of mind called the hard problem of consciousness, which is that it seems that there is a kind of cognitive gap, an explanatory gap between how we think about what it means for something to be physical and how we think about what it means for something to be mental. It seems there is something qualitative about mental states that put them apart from physical states. But interestingly, when you look at the literature, usually philosophers, they define what it means to be physical in a way that might look a bit naive from the point of view of physicists, because they either appeal to concrete objects or spatio-temporal states. There is always a reference to spatial localization. So there is an identification between being physical and being fundamentally spatio-temporal. So it appears that if space-time is non-fundamental, our grip on the physical becomes unstable, and the classic explanatory gap between the physical and the mental loses its footing. Right, so there are different strategies to go there. One might reply that, well, but it was just a bad and naive conception of the physical. The physical is not to be identified to the fundamentally spatio-temporal. But still there is a puzzlement about how to relate the mental to the physical. In a sense, yes, but it's a weaker gap because it's more a negative gap. We just want to say, even though we don't understand what it means to be physical, for the world to be physical fundamentally, we still think that there is something really a big tension between mental states and the physical world. But at the very least, we think that, well, if you don't have any positive conception of the physical, well, then it's quite difficult to stipulate that there is a conceptual gap. So it weakens dualism because traditionally this kind of gap between the mental and the physical is taken to be a motivation, an argument in favor of Alice property dualism. So the view that consciousness and mental states are really distinct from the physical states. And so by going against, by undermining this kind of motivation for dualism, you kind of provide an indirect motivation for non-spatial temporal monism, which is kind of an umbrella term for any view in the philosophy of mind that is not dualist. There are many different views. Some are a bit more radical, and some might say crazy than others. Right? You can maybe a panpsychist think everything is conscious everywhere, or an idealist. But there are more mundane standard options, namely physicalism and perhaps neutral monism, which is the idea that, well, everything is physical, full stop. All right. And so a second implication for the nature of abstract objects. So there is a debate in the ontology or the metaphysics of abstract entities, like mathematical entities or propositions or set theoretic structures. There is a debate about what their status are. For instance, the mathematical entities real, living in the domain on their own, or either could we reduce them to physical facts, right? And so there is an influent tradition, namely nominalism, which that goes back to Aristotle and medieval discussions, where the aim was to show how it was possible to reduce, for instance, the mathematics to the physics, but basically to get rid of any abstract objects. Or for instance, in formal logic, there was this debate between in the Polish school, they were trying to use merology instead of set theory to avoid committing to the empty set that look very abstract-like, and to get rid of those kind of weird abstract entities. But quite interesting, usually the nominalist programs, they try to reduce things to things or events located in space and time. So it seems that if space-time is not fundamental, you it will interfere with this nominalist program in many interesting way. While if you're a Platonist, so you think that mathematics, there is a mathematical world, or on Aristotelian, you think that there are mathematical properties at least instantiated by physical objects, but you do have distinctively mathematical properties. If you think that math exists over and above the physical, then you won't be really affected directly by this pressure on nominalism. But no, one interesting thing, if you think that if you move from this idea that space-time emerges from the fact that space-time is contingent, so that it could have failed to emerge, right? So we could have been in a according to the laws of nature and the material content in the world, it could have been the case that space-time would have not emerged. Then it means that nominalism is at best contingently true, because it can only be true in worlds where you have enough structural space-time to reduce the abstract entities to the physical spatial-temporal entities. So as I said, there is an asymmetry here with Platonism and Aristotelianism. But let's be careful here, because there are subtleties. So strictly speaking, fundamental eliminativism is incompatible with standard nominalism. If you think of standard nominalism as this view that you should be able to reduce everything abstract to fundamental spatial-temporal entities. right? Because someone might say, well, hey, look, I can still reduce abstract entities to derivative spatial-temporal entities, but it's not clear how that would make that would do the job. Perhaps it would, but it seems there is a missing stage in the argumentation to show how the derivation can go to the bottom. So overall, there are two different options. So either that's kind of an argument against spatial-temporal nominalism, and so against nominalism in general, or it's more an argument to think differently of nominalism and suggesting new ways to nominalize theoretical frameworks. So perhaps what should be done in the end is to try to relate abstract entities to a theory of quantum gravity that is not spatial-temporal without the mediation of the spatial-temporal physics. All right. Yes?
So you're talking about nominalism and Platonism, or is there a third position where maths is like a language that we use to understand things and does not necessarily latch or the emergent?
That would be right. That would be nominalism. I mean, basically, nominalism could also be called anti-realism, and Platonism is realism. So right now, what I'm mentioning is really about the existence. So when you say that mathematics is just a language, you are basically saying that the nature of mathematics is to be linguistic. But then there is this question about how do you think of the ontology of the language itself, right? So again, either your language is some kind of abstract, because you might say the language is made of propositions, sentences, but those things are themselves abstract. And then you will be on the side of Platonism. But if you think, no, the language is a kind of abstract entity that should be eliminated. So we use sentences, but the sentences don't really latch onto abstract propositions that exist. And then you will be on the side of anti-realism, nominalism. So I will... so I guess what you call a third position may be interpreted in two ways. Yeah. All right, so I'm going to stop. I just had some note on, just very quickly, you might also think that, because there is another third view, but quite crazy, which is the idea that the physical world is made of mathematical stuff, called the Pythagorean view. If you think that concreteness is defined in terms of spatial temporality or fundamental spatial temporality, and we don't live in a world where there is something like that, you might think that spacetime emergence puts pressure on the very distinction between the concrete and the abstract. And so that might provide a kind of motivation to think that everything is abstract instead of thinking that everything is concrete. But just wanted to mention this in passing. Once again, it's one of those cases where I put things on my slides I don't believe in. All right, so just to conclude, spacetime emergence could redefine discussions, both in physics and metaphysics. We think it comes with different, the implications will vary greatly depending on the degree of radicality of the approach of quantum gravity taken. So a revolution is of course not certain, but the potential is high, and I think we are absolutely right to work on those questions. Thank you very much.